Okay, well, welcome everybody. So we gave another webinar just over, well, maybe it's about 2 months ago now. We introduced the technology, but for any of you that missed it, we'll do another brief intro. But today I'll talk a bit about how, depending if you're looking at groundwater or soil, you're going to get different stories out of either of those. So the purpose of today's webinar is to hopefully relay some information that is, resonates with you. And I feel like if you're managing a site portfolio, you're a consultant, you're a technical expert, or you're just interested in the sensors, I think that this webinar should be for you, and hopefully you find it useful. So the topics we'll talk about, like the title of the presentation, groundwater and soil, and how we can incorporate a whole bunch of data into, well, today it'll be a groundwater model that essentially, summarizes your site very nicely for you, and how that facilitates quicker decision making, which we'll call adaptive site management. And what does Schrodinger's cat have to do with NSAID? Well, nothing really, but it's an analogy that resonates with me for talking about the process. So we'll try it out, see if it falls flat. And then I'd be happy to take any questions or any feedback that anybody might have. So in case you're unfamiliar with EMS, I'm guessing a lot of you followed us on LinkedIn. With our, mostly from our CEO, Dr. Steven Siciliano, who's an industrial research chair at the University of Saskatchewan, and also, of course, the CEO of the company. Overall, we've got about 10 years of R&D experience into monitoring with sensors. And these sensors have mainly been deployed at contaminated sites, where we've got some technology that we're using for quantifying soil health and variable rate technology optimization. So the 4 R's of fertilizer, and then also greenhouse gas emissions monitoring, all the way from the prairies up to Antarctica and the high Arctic. And so this is the type of tech that can be used across multiple different sectors. And some of the big value that I think is provided by these is that these sensors continuously measure. So you're getting a measurement every half hour, 24 hours a day, 7 days a week, unless something gets struck by lightning. And that's very helpful in continuously quantifying your hydrocarbon plume and how the mass is changing. And then if your measurements aren't too few and far between, if you're continuously monitoring, this means you get a more robust picture of what's going on at your site relative to point in time estimates. And this makes for better, another support tool in your toolkit, and you get more data for less money per data point. And of course, we've always got to make sure that we're being open and honest with the regulators. So if you've got continuous data rolling in, that facilitates quicker discussions with the regulators. So that's the preamble. So we'll do a little review of what the technology is in case you weren't here for the last one. So we call it our soil sense and our water sense. And let's see, I'll go to a laser pointer here. So you'll see on the bottom right here, this is our sensor pack. It's in this subtractive printed or machined plastic enclosure that basically keeps water out but allows gas through this membrane here. And here's the printed control board that contains all the instrumentation. And we'll look at what a full sensor setup looks like in a couple of minutes. But the secret sauce, or not so secret sauce, because this technology isn't real new. It's just a non-dispersive infrared sensor that works by shining an infrared light at a set spectrum through this gas sampling tube, where it's detected at the other end, and any attenuation in that signal is related to the gas molecules that geared your sensor to. So you can use different wavelengths of light depending on which gas you're interested in. Our sensors, depending which one, they measure carbon dioxide, methane, total petroleum hydrocarbons, and nitrous oxide. And then there's some additional data that we measure, like oxygen, which is important for natural source zone depletion, relative humidity, which is important for determining soil permeability or how well gases flow through soil. And also we can measure soil or groundwater salinity through sensors that we can add on. So just rotated the sensor here. And on the left and the right are two different setups we've got. So the one on the left here is our soil sense. And this is what we use to measure natural source zone depletion. And there's different installation options. If, when we first started off, we only did solar. We got a solar panel stick up at the top. These go down existing groundwater wells, and you'll see this white shaded region just blows up here. This is where the sensor packs are. And each sensor pack is separated at depth with a bentonite seal so that you're actually measuring the gases at that depth and not some flux from somewhere else. And this allows you to leverage the concentration gradient method of NSID, which I'll talk about briefly in a couple of minutes. So you got sensors at 3 levels, which allows you to calculate the gas flux and look at depletion. And so this setup, the soil sense will sit above the water table. They'll be measuring depletion in the soil. Whereas we've got another option, our water sense. It's the same tech, but it gets installed into the groundwater. So if you're interested in looking at how hydrocarbons are changing within the groundwater, and something we can do here in this example, it's the flush mount option. If it has to go into a parking lot, you need to be able to drive over it. That's something that this tech lends itself to. And so call it a midlife crisis, call it too much of an obsession with Super Mario Brothers. But we're going to try this analogy out today. So this actually started from, there's this really interesting read out there about groundwater modeling by Jeremy White, I think out of the southern US, about forecast first. So normally what happens in modeling is you've got a client, say, okay, we want a groundwater model. Okay, you do a whole bunch of modeling, you do a whole bunch of history matching, you make sure that you can recreate previous conditions. And once you've created this model, and it often takes a lot of time, then you start talking about, okay, what can we use it for? And Jeremy argues that this is a little bit backwards, that depending on the needs, you should really have these upfront conversations that, what's the most important metric at the site? Is it stability? Is it fence lines? So arrival of, if the plume's mobile, it arrives at some critical receptor. Or is it, do we have multiple sites that we just want to be able to, triage, to be able to send consultants out to sample? We can't sample all of our sites. We just need a couple. So, there's going to be a different objective depending on the site. So that conversation should really happen first before any modeling even gets started. If you need a mushroom, but you've built a flower, then that's not going to be helpful. And then hopefully by the end, you'll be convinced that any groundwater model should really incorporate soil modeling as well. Okay, so this brings us to unearthing the mystery of, well, what the heck is that title of this presentation? Groundwater and soils tell us 2 different facets of a contaminated site. So it boils down to groundwater is about risk mitigation and soil is about remediation. So because groundwater is the vector that will allow that product release to move, within a site or off a site, that's your risk vector. And remediation will deplete the source, but until you've pretty much removed the source from the soil, it's always going to act as a supply to the groundwater. So the groundwater might not be expected to change too much. So this is just illustrating the risk vector that groundwater represents. That ideally you don't see something like this where you have a release and it's moving off site and it's going crazy. So the soil modeling is about removal of the source, that you're not going to see a change in groundwater until you remove that source. And active remediation approaches like an SV or an MP are great for a couple of years, but then You start seeing diminishing return after that. I often just think of the, drinking your Slurpee and to form that cone around the straw. You're just not able to suck much up after that. And also these setups, they're very helpful, but they can be very expensive. I was actually amazed how expensive these are. So you don't want to have to use them for longer than is necessary. And then once maybe active approaches aren't paying off as much, then passive approaches like natural source zone depletion are great. And they're also great for if you want to have an A/B comparison for how an active remediation approach is going. If you're going to put in an SBE, you can measure natural source zone depletion before, then put it in and measure it after, and you've got a nice comparison to be able to quantify how successful the system is. So ideally, you're seeing something like this. So this is from our sensors at one of our sites where you've got an estimate of the aerial extent of the plume on the Y, and then date on the X here. And you can see there's a lot of variability, but if you fit a trend line to this, that it's going down through time, so it's a good news story. But just to highlight the value of how continuous data paints a different picture than point in time, if you say had sampled here and here, you might get the story that, oh no, something's going really, really sideways at our site. We really need to look into that. Or if you sampled here and here, you think, oh, our site's going to be clean in 2 years, when in reality, the story's somewhere in between. And you wouldn't have got that if you didn't have continuous monitoring. So I'll talk a little bit about the groundwater modeling approach. So we'll talk about the inputs first. So we can go to Environment Canada, we can get temperature and precipitation, which are really helpful for modeling groundwater recharge. Got our soil sensors, which gives you your depletion estimate. And then there's these fantastic sources of information. The phase twos and other consultant reports are just a wealth of great point in time information. So Hydrus is a publicly available modeling environment for 1D flow of water. So this is what you use to essentially use it for groundwater recharge. It's vertical, it's in the vertical direction. This goes into what's called mod flow, excuse me, and it's the USGS standard for building hydrologic models. And so this isn't something that we've made. This is an off-the-shelf model that we've employed into our workflow. And then we've got this other component of it. It's modular because you can add on bits, and we've added on this MT3 DMS. It's a groundwater solute transport simulator. So you get the idea of how your groundwater is flowing. That gives you an idea of how the solutes are transporting through that. And then these contaminant estimates that are gotten from these reports can be updated with a water sensor that measures in real time. And this, you'll see, maybe I use a few too many analogies, but this just makes me think of bowling with bumpers, that you get your initial model estimate off of the reports, and things change through time, or say there might have been some measurement errors. That initial release of the bowling ball down the bowling alley, if it's wrong, it's going to veer way off course by the time it gets close to the pins. But if you're able to nudge it as it goes along with real-time updates, and in the case of groundwater modeling, it's our water sensor, then you'll get much more realistic estimates of what the groundwater is doing, and hopefully get closer to that strike. And then finally, from these model outputs, there's all sorts of things you can do. You can look at how the area changes over time, concentration versus time, how stable the plume is. You can look at velocities. When does it get to some critical receptor on site? And then this can be an iterative process, talking with the client to see how, okay, what is the most important metric we need to get out of the site? What should we focus on? So I went through this in a very left to right format, but really, you should see what your inputs are. You have your discussion, what should the output be? And that's really going to dictate what sort of model that you build. And I feel like that's how you get the most leverage in decision support out of these, is to have those upfront discussions. So in a couple of minutes, we'll look at some results, and the main metrics that we'll focus on are plume stability. And obviously we need to define this. So we have area and concentration changes through time. And we look at when do those change by less than 1% per year. And so we consider that once the plume is stable. Or fence line arrival. Here we've got a cartoon of a site with a release on there. You can see the dash line is a property line. Say you're interested, okay, when does it cross the property line? When is it not in my backyard anymore? So we'll call that fence line arrival. And we'll look at 3 scenarios. We've got baseline where there's no depletion estimate. So we're assuming that NSD is 0. 1 where we've estimated NSD using our sensors at the site or our network of sites. And then a biostimulation scenario where we've applied an amendment solution to biostimulate the microbes to degrade the hydrocarbons on site. So I feel like most people are probably pretty familiar with NSD, but just in case, we'll just do a quick shallow dive into it. So we've got this site profile here. Say there's been a product release, it's made its way down to the water table. And that's where it's moving around. And this water table can raise and lower in your smear zone, smearing the hydrocarbon impacts in the soil. And atop this plume here, if you were to put sensors above it, you could measure these gaseous gradients. So you're having CO2 produced through aerobic degradation. You've got methane produced through anaerobic. You got methane oxidized to CO2. So anyway, you've got methane and CO2 being produced, and you've got oxygen being drawn down. It's being used to degrade these. So atop the spill, you'd have these steep gradients. Here's CO2 going up as you go down. Oxygen is going down, and then you have this steep gradient in methane and the volatiles. Whereas if you were, just off this area, you have a background site that you can use to correct for that. For any natural soil respiration, you'd have much shallower gradients. You still get an increase in CO2, still a decrease in oxygen, but just not quite as much. And I'm not going to dive into the chemistry, but basically use these 3 sensors to calculate gas flux. And from that, using the stoichiometry, in this case, we're comparing it to benzene, you can determine how much of that product is being depleted and at what rate. Okay, so we'll try this. So this is probably going back to high school chemistry, which is more recent for you guys than me, probably for the most part. So Schrodinger's cat, it was this thought exercise where you've got a cat, it's in a container, it's being exposed to a very high dose of radiation. And until you observe it, you don't know if it's live or dead. So is the cat alive? Is it dead? We don't know until we observe it. So it's a 2-state system, live, dead, and it depends on observability. So I'm maybe stretching a bit here, trying to apply it to natural source zone depletion. But this is a continuous system that relies on observability. We know depletion is occurring, but we need to quantify it. So until we've quantified it, we basically have to assume it's 0. So rather than a switch where it's live or dead, here it's more of a knob. So we'll call this Schrodinger's Goomba. We'll keep the Super Mario Brothers theme going. That likely it's some non-zero number. We don't quite know what it is. And if we don't incorporate this into our groundwater modeling, we're overestimating what our plume size is going to be in time. But if we include that NSD parameter, we're reducing our plume size, and that means that we're actually reducing our risk, which is a good thing. So here's our state of sites now. We've got sites across Western Canada and into Ontario there as well, where we're measuring natural source zone depletion. We've also got some vapor intrusion and groundwater sites, but we'll be focusing on these soil sites. So we've measured NSD at all these. This is what the regional mean natural source zone depletion looks like from those sites. This is for January to January, so it's a calendar year. And we've normalized it so that because sites are going to be higher and lower, but they're going to exhibit similar patterns through time. So we just want to be able to compare apples to apples. So that's why you see some negative numbers here. But we'll just look at the shape, and it's a little counterintuitive because if you read the literature on NSAID, normally you should be expecting to have, peak in the fall, say September, October, but that isn't really the case. On average, it's actually more in the springtime. And so that's our regional mean. If we look at a couple of sites, we see overlaying the regional mean there that some of our sites show this. Okay, that makes sense. I mean, we are calculating a mean, but there are some sites that are completely the opposite. If we overlay that regional curve on there again, you can see they're doing the exact opposite pattern. Still potentially a peak in NSAID in spring, but just the variance through time is much different. And so this I think highlights why it's so important to measure NSAID at a site and not assume that you say, okay, it's going to be highest in the fall. We'll assume that we'll measure then. See, there's actually a lot of variability. So this is where point in time estimates might fall a little bit short of giving you an accurate site picture. And the bonus, if you're measuring both hydrocarbons and their biological indicators of depletion, you get two estimates of how depletion is going at the site. And there's a nice relatively tight relationship. I've got to update this with our recent sites, but it's nice to see that NSAID is correlated with hydrocarbon depletion, which is what you'd expect. Okay, there's been a lot of buildup, Steve. Let's get to these models. So here's our three scenarios. On the left, we've got the baseline. In the middle, we've got, so baseline is where we're assuming NSAID is 0 because we haven't measured it. Here's where we have measured it. We've assigned it a non-zero value. And then on the right is the biostim. And this is, if we've got data at a site, we'll use those data, but based on averages across comparing biostim to non-biostim sites in our network, it's on average about a doubling of NSAID. So that's typically what this represents. And you'll see, hopefully it's not squinting too much, there's these light blue arrows. That's the groundwater flow. And then we've got these different isolines of groundwater concentrations of benzene. In this case, we've used, this is Alberta Tier 1 drinking water guidelines, it's 0.05 to delineate. And you'll see with the baseline scenario, the concentrations go down through time. You see the ticker going here. And that's mainly due to diffusion and dispersion. You're spreading out the same concentration over a larger area, so the concentrations are going down, but your plume is still getting bigger. With NSAID incorporating that depletion parameter, it's still growing, but it reaches a point, an inflection point where the plume actually starts shrinking. And biostim, see, this is a site where we did measure it. This is a nice success story where it actually is very effective, and that plume shrinks a lot quicker. So if you boil down the stats or the numbers from each of these, the time to stability, so that's when concentration and area are changing by less than 1%. Comparing your baseline, sort of your worst case scenario, to biostim, you've dramatically improved your time to stability by biostimming, and also dramatically reduced the total mass in groundwater. So as an outlook, for single site planning, look, okay, this actually looks like a really good candidate to either start biostim or continue biostimming at. So we can use this modeling framework in a different way. Let's say that we've got two sites and we know we need to sample at one, or we've got active remediation that needs to be deployed at one of these, and we can't decide which site it has to be. Well, we can run these models. And in this case, we're looking at fence line. So we've drawn a line around here that represents a land use change that we don't want to get off of industrial land use. And you can see the ticker going down. It's all the same scenarios. There's not a lot of difference. This, I think, due to the nature of the soils and the high concentrations, it might not be a good candidate for biostim. And there's not a lot of difference between the baseline scenario and biostim. and also in terms of, so that's for fence line and also in terms of time to stability. But it looks like it's going to take, several decades for that plume to reach, that critical receptor at the edge of the site. So there's some time. We can look at a different site, and the plume's moving a lot faster. It's the same situation. Biostim might not be the answer, but it looks like there's a lot shorter time window to when it gets to a critical receptor. So that might be, if you had to put resources towards one site out of these two, it'd probably be this one. This one, through the modeling exercise, you learn that, oh, there's actually there's some urgency. Okay, so we're in the home stretch, and then we can gear into some questions. The biggest thing is ultimately what we want to provide here at EMS is the most leverage for decision support you can get. So if you're interested in plume stability, we'll make sure that the models reflect that. If it's site triage, we'll use drugs to represent that. We'll do that. So you want to have these upfront conversations to basically blueprint out really what is the most important thing to come out of these models before you start building them. So just recapping, the groundwater modeling is about that changing risk vector, and soil modeling is about remediation, and that these two are intimately related, that until you remove that source of contaminants to the groundwater, you might not see appreciable decline in your groundwater concentrations. And the groundwater models are great, but they should really incorporate that soil modeling, that natural source zone depletion estimate to better match what's going on, better match the observations of the site. And if you've got more data, and also data that you can couch into an easily digestible format that we've all read, a lot of phase twos, which they're such a great repository of information. They're so invaluable, but they're very dense. So if you had to read 10 of them in a day, it would be tough. But if you could look at 10 groundwater models in a day, you might be able to make some evidence-based decisions a little bit faster. So you're still leveraging the same information, it's just sort of delivered in a different way. So we can stop there. I'd be interested in any feedback that anybody has, and happy to take any questions. And I can put this slide up for a second. If you don't get your question answered today, if it doesn't come to you, it sort of pops into your head later, you can feel free to reach out on LinkedIn, or here's my contact information and the CEO, and be happy to chat with you.